and what we were trying to do. And it's hard to imagine that you could see that first virtual fighter scene come alive, and that same company believed that we would be here today. It's just a really, really incredible journey. I want to thank all the NVIDIA employees for everything that you've done. It's really incredible. We have a lot of industries to cover today. I'm going to cover AI, 6G, quantum, models, enterprise computing, robotics, and factories. Let's get started. We have a lot to cover, a lot of big announcements to make, a lot of new partners that would very much surprise you. Telecommunications is the backbone, the lifeblood of our economy, our industries, our national security. And yet, ever since the beginning of wireless, where we defined the technology, we defined the global standards, we exported American technology all around the world so that the world can build on top of American technology and standards. It has been a long time since that's happened. Wireless technology around the world, largely today, deployed on foreign technologies. Our fundamental communication fabric built on foreign technologies. That has to stop. And we have an opportunity to do that, especially during this fundamental platform shift. As you know, computer technology is at the foundation of literally every single industry. It is the single most important instrument of science. It's the single most important instrument of industry. And I just said, we're going through a platform shift. That platform shift should be the once-in-a-lifetime opportunity for us to get back into the game, for us to start innovating with American technology. Today we're announcing that we're going to do that. We have a big partnership with Nokia. Nokia is the second largest telecommunications maker in the world. It's a $3 trillion industry. Infrastructure is hundreds of billions of dollars. There are millions of base stations around the world. If we could partner, we could build on top of this incredible new technology, fundamentally based on accelerated computing and AI, and for the United States, for America to be at the center of the next revolution in 6G. So today we're announcing that NVIDIA has a new product line. It's called the Nvidia ARC, the Aerial Radio Network Computer. Aerial RAN Computer, ARC. ARC is built from three fundamental new technologies: the Gray CPU, the Blackwell GPU, and our ConnectX, Mellanox ConnectX networking designed for this application. And all of that makes it possible for us to run this library, this CUDA-X library that I mentioned earlier called Aerial. Aerial is essentially a wireless communication system running on top of CUDA-X. We're going to create, for the first time, a software-defined, programmable computer that's able to communicate wirelessly and do AI processing at the same time. This is completely revolutionary. We call it NVIDIA ARC. And Nokia is going to work with us to integrate our technology, rewrite their stack. This is a company with 7,000 fundamental, essential 5G patents. Hard to imagine any greater leader in telecommunications. So we're going to partner with Nokia. They're going to make NVIDIA ARC their future base station. NVIDIA ARC is also compatible with AirScale, the current Nokia base stations. So what that means is we're going to take this new technology and we'll be able to upgrade millions of base stations around the world with 6G and AI. Now, 6G and AI is really quite fundamental in the sense that for the first time, we'll be able to use AI technology, AI for RAN, to make radio communications more spectral efficient. Using artificial intelligence, reinforcement learning, adjusting the beamforming in real time in context, depending on the surroundings and the traffic and the mobility, the weather. All of that could be taken into account so that we could improve spectral efficiency. Spectral efficiency consumes about 1.5% to 2% of the world's power. So improving spectral efficiency not only improves the amount of data we can put through wireless networks without increasing the amount of energy necessary. The other thing that we could do, AI for RAN, is AI on RAN. This is a brand new opportunity. Remember, the internet enabled communications, but amazingly smart companies, AWS, built a cloud computing system on top of the internet. We are now going to do the same thing on top of the wireless telecommunications network. This new cloud will be an edge industrial robotics cloud. This is where AI on RAN, the first is AI for RAN to improve radio spectrum efficiency. The second is AI on RAN, essentially cloud computing for wireless telecommunications. Cloud computing will be able to go right out to the edge where data centers are not, because we have base stations all over the world. This announcement is really exciting. Justin Hodar, the CEO, I think he's somewhere in the room. Thank you for your partnership. Thank you for helping the United States bring telecommunication technology back to America. This is really a fantastic, fantastic partnership. Thank you very much. That's the best way to celebrate Nokia. Let's talk about quantum computing. 1981, particle physicist, quantum physicist Richard Feynman imagined a new type of computer that can simulate nature directly. To simulate nature directly. Because nature is quantum. He called it a quantum computer. 40 years later, the industry has made a fundamental breakthrough. 40 years later, just last year, a fundamental breakthrough. It is now possible to make one logical qubit. One logical qubit. One logical qubit that's coherent, stable, and error-corrected. In the past, now that one logical qubit consists of, could be sometimes tens, sometimes hundreds of physical qubits, all working together. As you know, qubits, these particles are incredibly fragile. They could be unstable very easily. Any observation, any sampling of it, any environmental condition causes it to become decoherent. And so it takes extraordinarily well-controlled environments and now also a lot of different physical qubits for them to work together and for us to do error correction on these, what are called auxiliary or syndrome qubits, for us to error correct them and infer what that logical qubit state is. There are all kinds of different types of quantum computers. Superconducting, photonic, trapped ion, stable atom, all kinds of different ways to create a quantum computer. Well, we now realize that it's essential for us to connect a quantum computer directly to a GPU supercomputer so that we could do the error correction, so that we could do the artificial intelligence calibration and control of the quantum computer, and so that we could do simulations collectively, working together, the right algorithms running on the GPUs, the right algorithms running on the QPUs, and the two processors, the two computers working side by side. This is the future of quantum computing. Let's take a look.
There are many ways to build a quantum computer. Each uses qubits, quantum bits, as its core building block. But no matter the method, all qubits, whether superconducting qubits, trapped ions, neutral atoms, or photons, share the same challenge. They're fragile and extremely sensitive to noise. Today's qubits remain stable for only a few hundred operations. But solving meaningful problems requires trillions of operations? The answer is quantum error correction. Measuring disturbs a qubit, which destroys the information inside it. The trick is to add extra qubits, entangle, so that measuring them gives us enough information to calculate where errors occurred without damaging the qubits we care about. It's brilliant, but needs beyond state-of-the-art conventional compute. That's why we built NVQLink, a new interconnect architecture that directly connects quantum processors with Nvidia GPUs. Quantum error correction requires reading out information from qubits, calculating where errors occur, and sending data back to correct them. NVQLink is capable of moving terabytes of data to and from quantum hardware, the thousands of times every second needed for quantum error correction. At its heart is CUDA-Q, our open platform for quantum GPU computing. Using NVQLink and CUDA-Q, researchers will be able to do more than just error correction. They will also be able to orchestrate quantum devices and AI supercomputers to run quantum GPU applications. Quantum computing won't replace classical systems. They will work together, fused into one accelerated quantum supercomputing platform.
Wow, this is a really long stage. You know, CEOs, we don't just sit at our desk typing. This is a physical job. So today we're announcing the NVQLink. NVQLink. And it's made possible by two things. Of course, this interconnect that does quantum computer control and calibration, quantum error correction, as well as connects two computers, the QPU and our GPU supercomputers, to do hybrid simulations. It is also completely scalable. It doesn't just do error correction for today's number of few qubits. It does error correction for tomorrow, where we're going to essentially scale up these quantum computers from the hundreds of qubits we have today to tens of thousands of qubits, hundreds of thousands of qubits in the future. So we now have an architecture that can do control, co-simulation, quantum error correction, and scale into that future. The industry support has been incredible. Between the invention of CUDA-Q, remember, CUDA was designed for GPU, CPU, accelerated computing. Basically using both processors to use the right tool to do the right job. Now, CUDA-Q has been extended beyond CUDA so that we could support QPU and have the two processors, QPU and the GPU, work and have computation move back and forth within just a few microseconds. The essential latency to be able to cooperate with the quantum computer. So now CUDA-Q is such an incredible breakthrough adopted by so many different developers. We are announcing today 17 different quantum computer industry companies supporting the NVQLink. And I'm so excited about this, 8 different DOE labs. Berkeley, Brookhaven, Fermi Labs in Chicago, Lincoln Laboratory, Los Alamos, Oak Ridge, Pacific Northwest, San Diego National Lab. Just about every single DOE lab has engaged us, working with our ecosystem of quantum computer companies and these quantum controllers so that we could integrate quantum computing into the future of science. Well, I have one more additional announcement to make. Today, we're announcing that the Department of Energy is partnering with Nvidia to build 7 new AI supercomputers to advance our nation's science. I have to have a shout out for Secretary Chris Wright. He has brought so much energy to the DOE, a surge of energy, a surge of passion to make sure that America leads science again. As I mentioned, computing is the fundamental instrument of science, and we are going through several platform shifts. On the one hand, we're going to accelerated computing. That's why every future supercomputer will be GPU-based supercomputer. We're going to AI, so that AI and principled solvers, principled simulation, Principal physics simulation is not going to go away, but it could be augmented, enhanced, scaled, use surrogate models, AI models, working together. We also know that principal solvers, classical computing, could be enhanced to understand the state of nature using quantum computing. We also know that in the future, we have so much signal, so much data we have to sample from the world, remote sensing is more important than ever. And these laboratories are impossible to experiment at the scale and speed we need to unless they're robotic factories, robotic laboratories. So all of these different technologies are coming into science at exactly the same time. Secretary Wright understands this, and he wants the DOE to take this opportunity to supercharge themselves and make sure the United States stay at the forefront of science. I want to thank all of you for that. Thank you. Let's talk about AI. What is AI? Most people would say that AI is a chatbot, and it's rightfully so. There's no question that ChatGPT is at the forefront of what people would consider AI. However, just as you see right now, these scientific supercomputers are not going to run chatbots. They're going to do basic science. Science, AI, the world of AI is much, much more than a chatbot. Of course, the chatbot is extremely important, and AGI is fundamentally critical. Deep computer science, incredible computing, great breakthroughs are still essential for AGI. But beyond that, AI is a lot more. AI is, in fact, I'm going to describe AI in a couple different ways. The first way you think about AI is that it has completely reinvented the computing stack. The way we used to do software was hand coding. Hand coding software running on CPUs. Today, AI is machine learning, training, data-intensive programming, if you will, trained and learned by AI that runs on a GPU. In order to make that happen, the entire computing stack has changed. Notice, you don't see Windows up here. You don't see CPU up here. You see a whole fundamentally different stack. Everything from the need for energy. And this is another area where our administration, President Trump, deserves enormous credit. His pro-energy initiative, his recognition that this industry needs energy to grow. It needs energy to advance, and we need energy to win. His recognition of that and putting the weight of the nation behind pro-energy growth completely changed the game. If this didn't happen, we could have been in a bad situation. And I want to thank President Trump for that. On top of energy are these GPUs. And these GPUs are built into infrastructure that I'll show you later. On top of this infrastructure, which consists of giant data centers like easily, many times the size of this room, an enormous amount of energy, which then transforms the energy through this new machine called GPU supercomputers to generate numbers. These numbers are called tokens. The language, if you will, the computational unit, the vocabulary of artificial intelligence. You can tokenize almost anything. You can tokenize, of course, the English word. You can tokenize images. That's the reason why you're able to recognize images or generate images. Tokenize video, tokenize 3D structures. You could tokenize chemicals and proteins and genes. You could tokenize cells. Tokenize almost anything with structure, anything with information content. Once you could tokenize it, AI can learn that language and the meaning of it. Once it learns the meaning of that language, it can translate, it can respond just like you interact with ChatGPT, and it could generate just as ChatGPT can generate. So all of the fundamental things that you see ChatGPT do, all you have to do is imagine, what if it was a protein? What if it was a chemical? What if it was a 3D structure like a factory? What if it was a robot? And the token was understanding behavior and tokenizing motion and action. All of those concepts are basically the same, which is the reason why AI is making such extraordinary progress. And on top of these models are applications. Transformers is not a universal model. It's an incredibly effective model, but there's no one universal model. It's just that AI has universal impact. There are so many different types of models. In the last several years, we enjoyed the invention and went through the innovation breakthroughs of multimodality. There's so many different types of models. There's CNN models, convolutional neural network models. There's state space models. There's graph neural network models, multimodal models, of course, all the different tokenizations and token methods that I just described. You could have models that are spatial in its understanding, optimized for spatial awareness. You could have models that are optimized for long sequence, recognizing subtle information over a long period of time. There are so many different types of models. On top of these models, architectures. On top of these model architectures are applications. The software of the past, and this is a profound understanding, a profound observation of artificial intelligence, that the software industry of the past was about creating tools. Excel is a tool. Word is a tool. A web browser is a tool. The reason why I know these are tools is because you use them. The tools industry, just as screwdrivers and hammers, the tools industry is only so large. In the case of IT tools, they could be database tools. These IT tools is about $1 trillion or so. But AI is not a tool. AI is work. That is the profound difference. AI is, in fact, workers that can actually use tools. One of the things I'm really excited about is the work that Ervin's doing at Perplexity. Perplexity using web browsers to book vacations or do shopping. Basically an AI using tools. Cursor is an AI, an agentic AI system that we use at Nvidia. Every single software engineer at Nvidia uses Cursor. Has improved our productivity tremendously. It's basically a partner for every one of our software engineers to generate code. And it uses a tool. And the tool it uses is called VS Code. So Cursor is an AI, agentic AI system that uses VS Code. Well, all of these different industries, whether it's chatbots or digital biology where we have AI assistant researchers, or what is a robo-taxi? Inside a robo-taxi, of course, it's invisible, but obviously there's a AI chauffeur. That chauffeur is doing work. And the tool that it uses to do that work is the car. And so everything that we've made up until now, the whole world, everything that we've made up until now are tools. Tools for us to use. For the very first time, technology is now able to do work and help us be more productive. The list of opportunities go on, which is the reason why AI addresses the segment of the economy that IT has never addressed. IT is a few $1 trillion that sits underneath the tools of a $100 trillion global economy. Now, for the first time, AI is going to engage that $100 trillion economy and make it more productive, make it grow faster, make it larger. We have a severe shortage of labor. Having AI that augments labor is going to help us grow. Now, what's interesting about this from a technology